So it's important to understand some of the basics of the normal distribution, which is also called the z-distribution, since it will often make sense to assume that rates of return are distributed normally. So here we see a graph of a generic normal distribution. In the middle is the mean or average or expected rate of return. We'll call that R. And then as we move out by standard deviations. The units on the x-axis are the standard deviations that a certain point, a certain rate of return is away from our average or mean or expected rate of return R. And so as we move farther and farther out, you can move out incrementally, either positively or negatively away from that average return. And we have plus or minus 1 standard deviation away. Here shows plus or minus 2 standard deviations away, etc. And you can get all the numbers in between as well. There's such things as 1.5 standard deviations or 0.6 standard deviations. But as we can see, the normal distribution is symmetric, and that'll be important later on, we'll see. If our rates have a normal distribution, we know something about what percent of the data lies in certain intervals. The following lists the most common intervals. So if we're making a prediction about the future, and we say our best guess for what our rate of return is going to be is 10%. Well, we don't know for sure it's going to be 10%. There's some uncertainty there. But if we say that our rates of return are distributed normally, we can say, well, yeah, we think it's going to be 10%, but we're also 68.26% sure that the actual rate of return is going to be somewhere in the interval plus or minus 1 standard deviation, around that mean of 10%. And again, what a standard deviation is depends on the rest of our data, but right now we're just keeping it generic. It's just important to understand that these interval estimates, plus or minus 1 standard deviation, gives us some information about how likely it is the actual mean is going to fall in that interval. And so again, for plus or minus 1 standard deviation, it's 68.26%. We're that sure that the true mean is going to lie in that interval. For 2 standard deviations out, plus or minus 2, so the range is a total of 4 standard deviations, we're 95.46% sure that the true mean will actually lie in that interval. And finally, the most common one is plus or minus 3 standard deviations, and we're 99.74% sure that the actual mean will lie in this interval of plus or minus 3 standard deviations. So to find out how many standard deviations away from the mean a certain rate of return is, we use the following formula, and it's called a z-number. So the z-number, which we call z, is equal to the actual rate that we're trying to find, how far away it is from the return, from the mean return, so that's r, minus our expected or average or mean rate of return, r hat, divided by the standard deviation. This gives us the z-number, which tells us how many standard deviations away from the mean the observation lies. We could then use a z-table to find out what percentage of data lies above the number. So if it wasn't one of these clear-cut intervals, plus or minus 1, 2, or 3 standard deviations away, we would have to go to a table to find out exactly what percentage of the data is that lies above that z-number. Typically, z-tables show the percentage of data that lies above a specific z-number. But since the normal distribution is symmetric, we can still use a table like this even if we want to find the percentage of data that lies below a certain z-number. For example, suppose the mean rate of return is 8% and the standard deviation is 1.5%. We can ask the question, what is the probability that the observed rate of return will be greater than 10%? And so here again is our generic picture of a z-distribution. 8% is the mean rate of return, we put that right in the middle. 10% is above that, so we just put it to the right a little bit. We're not exactly sure where, but it's just somewhere to the right. And we need to find the z-number that goes with the rate of return, the observed rate of return of 10%. So again, here's the formula to find the z-number. It's the rate that you want, r, minus the mean rate of return, r hat, divided by the standard deviation. So we plug in our numbers, 10% minus 8% divided by 0.015, and we get a z-number of 1.33. So the rate of return of 10% is 1.3 standard deviations away from the mean of 8%. Now, if we look up the z-number of 1.33 in a z-table, we'll find that approximately 9.2% of the data lies in the upper tail, which means there's a 9.2% chance of our return being above 10%. And so again, the table gives us how likely it is that we'll get a piece of information that's in the upper tail of the distribution, above our z number. So the right tail is the 9.2%, which means that the rest of the interval, everything below 10%, is 89.8% of the data. So there's an 89.8% chance that a future observed rate of return will be below 10%. That's what this is telling us. We can also find the probability that a return will fall in between 2 points. Let's look at an example. Assuming the same mean rate of return of 8% and a standard deviation of 1.5%, find the probability that a return will be in between 7% and 9.5%. Well, again, here we just draw a graph to help us understand what's going on. The mean goes in the middle, it's 8%, 7% is somewhere to the left, and 9.5% is somewhere to the right. First, we need to calculate both z numbers that correspond with the 7% and the 9.5%. So here's the formula again. It's the 7% minus the expected rate of 8% divided by the standard deviation of 0.015. We see that the z number that goes with the rate of 7% is negative 0.67. We do the same thing and we find the z number for the 9.5% and we see that it's 1.0. So now we need to find their corresponding probabilities from the z-tables. So now we need to look in our z-tables and find what probability is associated with the z number of minus 0.67. Well, since the normal tables are symmetric, we can look up what the probability associated with the z number of positive 0.67 is. And that'll give us the probability in the upper tail region corresponding to the z number of 0.67. And we can then switch it and associate it with the lower tail region because we're associating it with a z number of minus 0.67. So basically, if you ever need to use the fact that the normal distribution is symmetric and you change the sign of the z number, when you get the data back, when you look up the probability, it switches from being an upper tail to a lower tail probability. So we look in our table and we see it's 0.251, 25.1% of the data is in the upper tail for a z number of positive 0.67. And again, this means that 25.1% of the data is in the lower tail when you look at the 7%, which has a z number of minus 0.67. So basically we know there's a 25.1% chance that return is going to be less than 7%. Well, since the area to the left of the mean is 50%, and again we know that because the normal distribution is symmetric, the area between 7% and 8% is the 50% minus the 25.1%, which gives us 24.9%. So again, we use that fact that the normal distribution is symmetric. We can just subtract and find that the probability that return is between 7 and 8% is going to be 24.9%. We need to do the same thing for our 9.5%, which we already found was a z number of 1. So we look up a z number of 1 in our tables, and the probability is 0.159. Now that probability goes in the upper tail, because that's what our z-table tells us, is the probability in the upper tail region based on a z number. So there's a 15.9% chance that return is greater than 9.5%. Again, since the area to the right of the mean is 50%, based on the normal distribution being symmetric, the area between 8% and 9.5% is the total 50% minus the 15.9% that's in the upper tail, and that gives us 34.1%. Thus, the probability that the rate of return will be between 7% and 9.5% is the 24.9% plus the 34.1%, or 59%. And that's the end of part 2.